Okay, we want to determine if this is a free body diagram problem or a non-free body diagram problem. So what we do is count the degrees of freedom. In this particular case, I'm going to assume that the crate does not leave the floor, it doesn't rotate, but it does slide. Later, I will demonstrate how to determine if that's true. So there's 1 degree of freedom. What this means is that you have to be given 1 acceleration in order to solve this problem. And if you read the problem, it doesn't really give you an acceleration. The other dead giveaway for needing a free body diagram is they ask you to determine the magnitude of the force. Whenever they ask you for a force, you're going to end up having to draw a free body diagram. So we're going to draw the free body diagram for this. And when you do that, you have to determine what you want inside the free body diagram. In this case, there's only 1 mass, so it makes sense that you would only draw a free body of that particular mass. Okay, if you recall, forces always come from action at a distance forces. There's 5 of those. The only one that we deal with in this class is gravity. In the case of gravity, the gravity, like all forces, occur between 2 objects. In this case, gravity occurs between the crate and the earth. The crate is inside the free body. The earth is not in the diagram, and so that's an inside-outside force, and that's why we draw it. So in this case, it would be mass times the gravity constant. After you find the action at distance forces, then you look for contact. There's contact that's occurring between the crate and the table. The crate is there's a pressure, which is normally called the normal force, and there is friction, which is tangent to the earth, parallel to the surface. Okay, so in the case of the normal, that force is caused between the crate and the table. The crate is in the diagram, the table is not, and so therefore we have inside-outside, so you have a force. In this case, normal forces are pressures, and so they push against each other. If there was a vacuum or something being sucked down through the, like a air hockey table, then there's possibility of having a normal force pulling the mass down. Otherwise, they push against each other. So the table pushes the block, so it goes up. In the case of friction, friction is parallel with the surface. In this case, it's sliding. Sliding friction is always μk times the normal pressure. So the harder you push, the greater the friction, or the harder the pressure, the greater the friction. Now, because you know the value of the friction, you have to know the direction. And so in this case, we need to determine the arrowhead. All right, now friction always opposes the slip. In this particular problem, if the mass is tending to slide, it's going to slide to the right. Friction doesn't like that, it wants to prevent that, and so it's going to pull the block back to the left. Always opposes the slip. You may have heard that it opposes motion. That's not true. I'll show you some examples later. The only other place that anything is touching is here at the rope. And the rope is between the crate and somebody's hand. And so it's an inside-outside, and that's why you draw it. So you have this force P at the angle of 30 degrees. Once you have the free body diagram, you always sum forces. In the real world, you'll always sum forces in 3 directions. But in this case, most of our problems, we'll run into a few later just so you can see, but in most of the problems, everything is 2 dimensions. And so I'm going to sum forces in 2 directions. The direction that you choose to sum forces in should always be chosen in a direction that makes acceleration easy to determine. In this case, think about the motion of this crate. If the crate moves, it's going to slide along the horizontal plane. So therefore, I'm going to sum forces horizontally and vertically. The third direction would be in and out of the page, which we don't really need to do because nothing's happening in that direction. Okay, so let's sum forces in the to the right. We're going to take as positive, and up we're going to take as positive. So horizontally, the forces are, okay, to cut down on time, I've gone ahead and written these. The forces in the x direction, there's positive P cosine 30, which is the force of the rope, and the rope is pulling to the right, that's why it's a positive number. The friction is pointed to the left is negative, that's why it's a negative. The acceleration, I don't know the direction. I mean, we do, but it's not given. So I'm assuming that the acceleration is to the right. That's why I put it in as a positive mass times acceleration. If I wanted to assume that the acceleration went left, I would put in a negative mass times acceleration. Typically, I always choose positive for the accelerations if I don't know them. And then the second equation is the summation of forces in the vertical direction, up being positive. So P force is pulling up, so that's why it's a positive. Gravity is pulling down, that's why it's negative. The normal pushes up. In this particular case, there's no motion vertically, and that's why the acceleration vertically is equal to 0. Okay, so now let's count the number of things we know or don't know, and we'll circle them. So I don't know P, that's 1. I don't know the normal, that's 2. And I don't know the acceleration, that's 3. Down in the bottom equation, I've already counted P, and I've already counted N. So I have 3 unknowns, and I have 2 equations. Now, some people will argue and say, well, you know the normal force. Well, do you really? But even if you did, even if you said you know the normal force, then that equation in blue right there is no longer any good for you, because the only thing it does is tell you what N is. And all it would do is it would remove one equation, remove one unknown. You're still one short. Okay, so the problem that you have is you have too many unknowns, not enough equations. You have to find another equation. Either that or the problem is undefined. So the way you look for more equations when you're doing free body diagrams is the first thing you look for is it possible to find another mass to draw a free body diagram of? In this case, the answer is no. There's only one mass, so there's only one free body. So rule that out. The second thing is to read the problem and identify if there are other things that are being given. So in this particular case, the answer is yes, because it tells you that it achieves a velocity of 4 when it travels a distance of 5. And we haven't used that yet. So what we want to do is use that information somehow to relate these. So I'm looking for an equation that is going to relate velocity and position. And so that's what I'm looking for. Now, when we started this, we didn't ask if it was a time spanner, should have, but this is a time spanner. Because it's a time spanner, the way you solve time spanners is you integrate something. And what I'm going to do is I'm going to, because I want velocity in position, I'm going to get above velocity. That means I'm going to get acceleration, and I'm going to integrate it back to find the velocity. So I don't really want to do that, and so I'm looking for a shortcut. I can use the handy formulas if the acceleration happens to be constant. In this particular case, it is, because if you look at the top equation here, the P is constant, 30 degrees is constant. All of these terms in here are constants. And because they're all constants, then when I solve for A, it would have to be a constant as well. So I'm going to be able to use these handy formulas for relating that. So I'm looking for an equation that relates velocity and distance. I have one memorized. It looks like this: v squared equals v0 squared plus 2 acceleration x minus x0. Let's plug in and see what we have. The final velocity is given to be 4. So this would be 4 squared. The initial velocity is 0, starts at rest. So that's 0. Plus 2. Now, what I want to do is I want to put in either a positive A or a negative A based on what I assumed last time. So you have to ask yourself, what did you think acceleration was doing before? I believe it was going to the right, which it is, but I plugged it in as a positive number. Before, I have to plug it in. I have to plug it in as a positive number again. So you have to be consistent. So this is A. I don't really know what A is. I'm just going to put it in this way. Okay, the X. The X is given to be 5. And the initial X, if you take the origin to be where it began, that'll be 0. Okay, so now let's go in and see if there's any more unknowns. The only thing unknown in this equation is acceleration. I've already counted that, so the number of equations that I have is the top one, the second one, and then this one here. So I've got 3 equations, and the number of unknowns is 3. So I have 3 equations, 3 unknowns. I can solve this now. What I'm going to do is I'm going to pull up Mathematica and demonstrate how to solve these equations using Mathematica. Okay, here I've got Mathematica pulled up, and the standard quit that you start off with at all times. Now I'm going to type in the equations that I have. I'm going to name this 1 equal sign because I'm naming it, not establishing an equation. Now I'm going to type in the equations. Let me zoom in a little bit. Okay, so the equations are P. Cosine is built in, it knows it, so I'm going to start off with a capital C for the cosine. Mathematica always uses radians and not degrees, so if you want to convert the 30 into degree, you use the word degree, 30 degrees. Mu k times n. If you notice, I'm using, whoops, I shouldn't use a capital there. I'm just using spaces instead of the stars for multiplying. And then this is an equation, so you have to use 2 equal signs. Mass times acceleration. Since it's a set of things, it begins with a curly brace, and we have a comma between the equations. Second equation, P. Sine starts with a capital because it is built in and it knows how to calculate that. 30 degrees minus mg plus n. 2 equal signs because it's an equation. The last equation, 4 squared, you probably just put in 16, equals, it's an equation, 2 times acceleration times 5. And that's it. So you end your curly brace, turns black, hold down shift, hit enter. These are the equations. You might want to spend some time, check to make sure they're okay, and then you're going to solve them. You say, what do you want to solve? I want to solve the equations. What do you want to solve for? There's 3 equations, so I have to find 3 things to solve for. I want to solve for P, I want to solve for A, and I want to solve for N. Alright, and I realize now that I should have defined these variables, so I'm going to go back and give this a name so that I can refer to it. So I'm going to say that's my answer. And now what I'm going to do is put in the values I know. So mu k is, according to the problem, 0.3. G, let's see, we are in meters, so that would be 9.81. And mass, okay, so mass is 50. Whoops. is 50. Notice that these are single equal signs because these are not equations. I'm just simply defining them. So I execute that, and then I just want to look at what my answer is. Bingo. And here you've got the values that you needed. Okay. All right, so that's the solution of this one. I'll post it for you.